is going to be our first video for our first lesson on the areas between curves. So this unit is going to be about applications of integration. So we just finished up our unit where we talked about how to find integrals, many different ways to find integrals, substitution, talked about area, total area, net change, net total area, all this stuff. And so this section or this unit is very quick. It's only 3 lessons, but they're going to be pretty involved, all 3 lessons. So this first one, we're going to talk about how to find the area between 2 curves, because we haven't done that yet, right? So far, all we've done is find the area between one curve and endpoints and the x-axis. So you can see here in the blue that if one of your functions is always above the other one, finding the area between the 2 curves is actually pretty straightforward. You're just going to find the integral of your limits of integration, and you subtract the highest one minus the lowest one. So let's try this one here. So the first thing I'm going to do is I'm going to go graph it. I know it's right here in the image. I'll go ahead and graph it for you on Desmos a little larger there. So x plus 4. And then the other one is 3 minus x over 2. All right. And we're looking at this one between 1 and 4. So let me do 1, 2, 3, 4. There we go. Right. Zoom out a little bit. There we go. Okay. So you can see we have x equals 1 and x equals 4. Change the color there. And once you look at it, right, you can see the shaded area between 1 and 4 between the 2 curves. And if you look, the one in red, which is x plus 4, and the one in blue, which is 3 minus x over 2, you can see that the in between 1 and 4, the red one is always above the blue one. So we're going to do the integral between 1 and 4 of the x plus 4 function minus the 3 minus x over 2 function. All right, so let's put that here in the first slide. Where'd it go? There it is. All right, so we have the integral from 1 to 4 of x plus 4 minus 3 minus x over 2. All right, now the first thing I'm going to do is I'm going to subtract like terms here. X minus negative x over 2, that's negative 1/2 x in there. So when you subtract a negative, you have addition. So 1 plus 1/2 is going to be 3/2 x. And then when you do 4 minus 3, you get 1. Now, we've done this before. This is going to be integration. So you're finding the antiderivative. All right, so the antiderivative is going to be start with x squared. So I need to put something in front that when I multiply it by 2, I'm going to get 3/2. So I know that that's 3/4. I'll show you in class how you can always set up a basic algebraic equation to find that if you don't know. Okay. So once I do that, then it's going to be plus x. All right. And I'm going to evaluate this at 4 and 1. So do f of 4 minus f of 1. Whatever I get there will be the area between these 2 curves. So that's going to be 3/4 times 4 squared plus 4 minus 3/4 times 1 squared plus 1. Again, feel free to go to Desmos at this point. I'm going to try to do it mentally for you. 4 squared is 16. 16 divided by 4 is 4. 4 times 3 is 12. 12 is 4, that's 16. This is going to be 1 squared, which is 1. 1 times 3/4 is 3/4. 3/4 plus 1 is 7/4. So 16 minus 7/4. If I change that, have denominator 4, that's going to be 64/4 minus 7/4, which is going to be 57/4 square units. Okay. Again, if you want to do the decimal's totally fine, guys. But that is the area between these 2 curves. All right. Okay, let's keep going. Now, the next kind of iteration of this is looking at the area between 2 curves, but the region is bounded by where they intersect. So you can see in this sketch here, in this graph, that we're looking at the area between these two functions, but we first need to find the limits of integration because right now I don't know where they intersect. You could type this into Desmos and you could literally click on where they intersect to find those x values. I'm going to do the algebra here to find it. So you're going to set them equal to each other. So 6 minus x equals 9 minus, and I'm going to go ahead and square this, x squared over 4. All right, I'm going to multiply everything by 4 so I can get that x squared to not have a fraction anymore. So 24 minus 4x equals 36 minus x squared. I'm going to get everything to one side and set it equal to 0. So that's a positive x squared when I move it over. That's going to be minus 4x. And then when I move the 36 over with subtraction, I get minus 12. Doing our factoring from algebra 2, we get, let's see, x minus 6 and x plus 2. So my limits of integration, or where these intersect, are going to be 6 and negative 2. And you can kind of see, eyeball it there in the sketch. So I need to find the integral from negative 2 to 6 of, and I'm going to do my subtraction again, the x squared minus over 4, I should write negative x squared over 4 plus 9 minus 6 minus x. All right, so let's do that subtraction. Good thing you have extra room. That's going to be negative 1/4 x squared. Let's see, subtracting a negative x actually becomes positive x, and 9 minus 6 is 3. So let's find the antiderivative. So this is going to be x cubed. All right, I need something that when I multiply it by 3, I get negative 1/4. That's going to be negative 1/12, because that would be negative 3/12, which is negative 1/4, plus 1/2 x squared plus 3x. So if I evaluate this at 6 and negative 2 and subtract them, I will get my answer. So I'm going to go ahead and, since I ran out of room, I'm going to use Desmos here and type this in. All right, so let's plug in 6 and negative 2 into this function. Okay, delete all this. So first I have negative 1/12 times 6 to the third power plus 1/2 times 6 to the second power plus 3 times 6, I believe. Let me confirm. Yes. Okay, so all of that, and then minus, do the same thing but with negative 2. So negative 1/12 times negative 2 cubed plus 1/2 times negative 2 squared, and then plus 3 times negative 2. Right? So the answer is 21.3 repeating, or 64 thirds. Your choice, 21.3 repeating or 64 thirds. They're both the same. And that's going to be square units. Okay, let's go to another one. All right. Now, the next kind of iteration of this, so far we've done between two curves, but it's where they intersect. And now we're looking at where you have the integral between two curves, but sometimes one of the functions is above the other, and on the other part of the interval, the other one is. So essentially, if you look at this sketch here between sine of x and cosine of x, we're looking at the interval between 0 and pi. And you can see at the beginning, we have cosine of x is above sine of x. And after that, we have sine of x above cosine of x. Let me show you in Desmos real quick. I'll graph sine of x and cosine of x from 0 to pi. Okay, let's change this to be steps of pi over 6. Let's zoom in for 0 to pi. Too far? Yeah, just barely. Zoom back out. Okay, so here's 0. Here's pi. And you can see we're looking at the area between the curves. So right now, at the very beginning, purple is above green. So cosine is above sine all the way until pi over 4. You should hopefully remember from your days in trig that the sine and the cosine of pi over 4 is actually the same, the square root of 2 over 2. And then from pi over 4 to pi, you'll notice that the green one, so sine, is above the purple one. So essentially what this means is when it says like this absolute value, like we talked about in problems in the last unit, is that essentially what this means is that we're going to need to break this up into multiple integrals. All right, so here's how I'm going to write it. I'm going to write down that the integral from 0 to pi of the absolute value of sine of x minus cosine of x is actually equal to two different integrals. Okay, so this is equal to the same thing as from 0 to pi over 4, and that's where cosine of x is above sine of x. And then plus the integral from pi over 4 to pi, where sine of x is above cosine of x. So it's kind of like doing two versions of what we talked about in our very first example. All right, so I need to integrate from 0 to pi over 4 cosine of x minus sine of x. So let's go ahead and find the antiderivative for that. Right, remember the derivative of, or the derivative of sine is cosine, so that's going to be sine of x. And the derivative of cosine is going to be the opposite of sine of x. So actually this is the first one here. Evaluate it at pi over 4 and 0. So I'm going to find that first. Let's do that. So that's the sine of pi over 4 plus the cosine of pi over 4, whatever that is, minus the sine of 0 plus the cosine of 0. All right, we know that these are both the square root of 2 over 2. And then that's going to be minus the sine of 0 is going to be 0. And the cosine of 0 is 1. All right, the square root of 2 over 2 plus the square root of 2 over 2 is actually just going to be, let's see, that's going to be 2 square root of just the square root of 2 minus 1. So this is equal to the square root of 2 minus 1. All right, so that's just like halfway done. Now I need to find the integral from pi over 4 to pi of sine of x minus cosine of x. All right, so let's do that. Antiderivative. We've got cosine, and the derivative of that would be negative sine x. So I need to put negative in front. And if I do the derivative of sine, I get cosine, but it needs a negative as well. So this is the antiderivative. And if you wanted to change the order, you could. Evaluate it at pi and pi over 4. So here we go. Let's do that. The opposite of the cosine of pi minus the sine of pi, so whatever that is, minus the opposite of the cosine of pi over 4 minus the sine of pi over 4. All right, so we got cosine of pi. Cosine of pi is going to be negative 1, and the opposite of that is 1. Sine of pi is going to be 0, so that's just going to be 1, minus, both of those are going to be the square root of 2 over 2, but we have negative square root of 2 over 2 minus square root of 2 over 2. So that's going to be negative square root of 2, so this becomes 1 minus negative square root of 2, which is the same as 1 plus the square root of 2. All right, so if I add those together, remember I have two pieces here, this piece and this piece. If I add those two together, I will get the answer. And when you add those together, the negative 1 and the 1 make 0. So the square root of 2 plus the square root of 2 is going to give us our answer. Let me see if I can write it somewhere for you. Let's see, where do I want to put this? I guess I'll just put it here at the very beginning. But the square root of 2 plus the square root of 2 is going to be 2 square roots of 2. So this is ultimately what the whole thing became. Okay? So that kind of shows you many different iterations for how to find the area between two curves. Okay, I'm going to move into finding the area between a complex region. Okay, so for this one, if you look at the sketch that's given to us, you'll notice that we have the area kind of looks like a triangle, and there really looks like two main areas here that I can split it up into. I'm going to use between 0 and 1, right, between 0 and 1, which is just the integral of the orange one, or x squared, and then between 1 and 2 is just the blue line and the x-axis, which is 2 minus x. So to find this area, I'm going to do two integrals. I'm going to do the first one, which is between 0 and 1 of x squared dx, plus the integral from 1 to 2 of 2 minus x dx. All right, so it's kind of like two different pieces to solve. So we know this one, the antiderivative here, is going to be 1/3 x cubed evaluated at 1 and 0. So we can find that real quick. So f of 1 minus f of 0, that's going to be 1/3 minus 0, or 1/3. Okay. This one, this antiderivative, is going to be, let's see, that's 2x. And then this is going to be minus 1/2 x squared. Okay. And that's going to be evaluated at 2 and 1. So we're going to do f of 2 minus f of 1. So let's see, 2 times 2 minus 1/2 times 2 squared, whatever that is, minus 2 times 1 minus 1/2 times 1 squared. Okay, so that's 4. The first part, 2 squared is 4, half 4 is 2. 4 minus 2 is 2, minus, that's going to be a half. 2 minus a half is going to be 1.5. Let's keep it as fractions. So 3/2. Okay, so when I subtract that, I'm going to have 4/2 minus 3/2, which is 1/2. So it ends up giving me 1/3 plus 1/2, which is going to be, let's see, that's going to be 2/6 plus 3/6, which is 5/6 squared units. All right, so that is it for the area between these kind of two curves, but also you can see it's kind of really like split into two separate integrals. Okay, now the very last thing we're going to do, which you are going to see on the AP exam, is that there's another way to do this kind of problem. All right, so this problem, which I'll show you on Desmos, a little bit easier to see, is you can actually, instead of doing the process we just did, you could actually integrate with respect to the other variable y. Okay, so this is kind of how the process that we do it. And I'm going to go to Desmos to kind of see if your brain can kind of rotate it, and so you can visualize what I'm talking about. So I'm going to graph x squared, and then I'm going to graph 2 minus x. So I'm going to graph x squared, and then 2 minus x. All right, let me change back to out of radians. All right, now, so what we just did was we found this area right here, okay? But if you just look at taking this and kind of rotating it, where now this is your x-axis and this is your y-axis, you should be able to see that this x-axis and this point where they intersect 1, 1, we have the area right here where one is above the other, okay? So the red one above the black one. So essentially what I'm going to do to solve this by integrating with respect to y is I'm going to take each of my equations, write them in terms of y, and then do the same process we did in terms of the very first problem. Okay, so here's my first step. My first step is to take y equals x squared, and then y equals, was it 2 minus x? Yes. And write them in terms of x by itself. So I'm going to solve for x by taking the square root. So we have the square root of y equals x. You'll notice I did not do plus or minus, because when you look at the sketch, I only really care about the positive part there. All right, so I didn't just ignore it, but I thought I don't actually need it. Then this one is going to be, let's see, move the x over, it becomes x equals, and then this becomes 2 minus y. All right, and so to do my integral with respect to y, I'm actually going to use 0 to 1. as opposed to what I used before, which was 0 to 2, because, again, I'll try to explain it in the sketch. But if you were to look, kind of rotate it, right, where this is the x-axis and this is the y-axis, we're only going up to 1 here where they intersect. So that's why I'm using 0 to 1. Okay, and I'm going to use the red one, which is 2 minus x, is above the one in black. So I'm going to do of 2 minus y minus the square root of y. Okay, now I'm going to find my antiderivative here, which is going to be 2y minus 1/2 y squared. And then remember, the square root of y is actually the same as y to the 1/2 power. So this is y to the 3/2 power times 2/3 in front, and I'm subtracting. And I'm going to evaluate that at 1 and 0. So f of 1 minus f of 0. Feel free to go to decimals if you want. I'm going to do the algebra here. So 2 times 1 minus 1/2 times 1 squared minus 2/3 times 1 to the 3/2 power. So all of that minus 2 times 0 minus 1/2 times 0 squared minus 2/3 times 0 to the 3/2 power. Again, you'll probably notice that all of that's going to become 0. So just focusing on essentially f of 1. So that's 2 minus 1/2, and then that's going to be minus 2/3. Let's get a common denominator, which is 6. So that's going to be 12/6 minus 3/6 minus 4/6. 12 minus 3 is 9. 9 minus 4 is 5. So you get 5/6 squared units. Shouldn't be surprised by that answer, since this was essentially the same problem, just completed in a different way by integrating with respect to the other variable y. Okay, so anyway, hopefully you'll see in a few weeks how we're going to do that in terms of questions on the AP exam. Good luck on the homework.